designed. And what's special about it is that it allows the cathode rays to be affected simultaneously by electric and magnetic forces. And the experiment that J.J. Thomson did with this tube would have the most dramatic consequences.
Thomson was not a practical man. In fact, he was notoriously clumsy. Yet using his new tube, he performed a series of hugely important experiments.
He would turn the cathode ray tube on. You'd see a glow and a bright point at the other end of the tube. Turn the electromagnets on. The position of the dot moves. The magnets are deflecting the cathode rays.
Thomson repeated the experiment time and time again and measured the size of the deflection. Whatever was coming down the tube was clearly not a wave. It only made sense if it was a stream of particles. Thomson then plugged the figures into Maxwell's famous equations.
And the result he got was absolutely dramatic. He found that the particles making up cathode rays are tiny, much, much smaller than atoms. And that was an earth-shattering result.
Nobody had ever produced any evidence that there was anything smaller than an atom before. Indeed, some scientists didn't even believe in atoms. Years later, Thomson was to describe his findings in a lecture to the prestigious Institute of Electrical Engineers.
Could anything at first sight seem more impractical than a body which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a crowd of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
Today, we know these tiny particles as electrons. This was really revolutionary stuff. And what was so exciting about it was that the technology to begin to pull atoms apart, to tell a story about the most fundamental building blocks of the world, came straight from optical engineering. Vacuum pumps, light bulbs, radiation tubes. It was by thinking about those bits of machinery that the atom began to be torn apart. Yet it's one of history's great ironies that at the time, nobody realized science was on the verge of a breakthrough that would turn physics and the world on their heads. By the end of the 19th century, most scientists in Europe and overseas reckoned that in many ways the task of physics was over. The basic problems had been solved. They believed they knew how light, electricity and magnetism worked and had overcome the problems of heat and engineering.
Physics turned into a search not for great new theories, but just for better measurements.
One of these measurements concerned the production of light bulbs, by now a hugely important and influential commercial activity.
the light and power system was the most important financial area of industry. Getting the right answer to problems of electric light and electric power meant big bucks worldwide.
The problem the industry faced seemed scientifically trivial.
What they wanted was to get the maximum amount of light out of a bulb for the minimum amount of electric energy going in. So the physicists were asked, do some sums and calculate what the relationship is between the amount of electric energy heating up a piece of metal wire and the amount of light coming out when that wire starts to radiate. No one thought that this was going to be a deeply important theoretical problem. It mattered to people's bank balances. It didn't seem to matter to physical theory very much.
The man the industry turned to was a German physicist called Max Planck. Planck looked at Maxwell's celebrated equations, which described the relationship between light and energy. It was then that he had a shock.
What these equations suggested was that the more energy you put in and the hotter the system got, the more light and heat it should radiate.
Maxwell's equations had predicted that the energy levels would continue to build up infinitely until an object was radiating a catastrophic amount of light and heat. And it would atomize. But this simply